Modern artificial intelligence infrastructure is designed to look sterile and effortless. Silent, glowing racks operate at the nanometer scale inside climate-controlled halls. But the history of this hardware is defined by a heavy, manual reality. In the 1940s, a computer was a room-sized machine that required a team of technicians just to keep its physical components from failing. This environment existed because every digital calculation relies on a simple binary choice. A circuit is either open or it is closed. To perform that choice, the machine must use a physical mechanism that acts as a switch. Because these switches are physical objects, they are subject to the limits of the material world. The evolution of computing is a century-long record of engineers fighting against friction, spatial constraints, and the constant generation of heat. Before the era of silicon, engineers used electromechanical relays to perform Boolean logic. These were heavy metal switches that physically snapped open and shut to move electricity through a circuit. These relays were slow and prone to mechanical failure. The constant friction of metal parts slamming together caused them to wear down, while the noise of thousands of simultaneous switches made these early computers deafening to operate. The introduction of the vacuum tube finally allowed engineers to remove the moving parts. By creating a grid that controlled a flow of electrons through a vacuum, they could switch currents at electronic speeds. This relied on thermionic emission, which turned the tubes into high-heat components similar to incandescent light bulbs. They consumed massive amounts of electricity, and the glass filaments frequently burned out, requiring the machines to be shut down for constant repairs. This thermal inefficiency created a new bottleneck. As computers grew more complex, the heat and fragility of the tubes became unmanageable, leading some engineers to look for ways to compute without using electronics at all. This search led to fluidic logic, an attempt to build computers without electricity. The concept utilized fluid dynamics, where a high-pressure jet of water could be used to deflect a secondary jet, creating a physical logic gate. The Soviet Union developed this into functional hardware with the Lukyadov hydraulic integrator. These were water-based computers that used fluid pressure and flow levels to perform complex mathematical integrations. This technology was valuable during the Cold War because fluid logic is immune to electromagnetic pulses and radiation that would instantly destroy standard electronic components. But water cannot be miniaturized to the same degree as an electron. Because fluid logic required pipes and physical valves, it could not scale down to meet the demand for smaller, more portable processors. At MIT, a young professor named Dudley Buck proposed solving the heat problem by moving in the opposite direction, toward the environment of absolute zero. Buck developed the cryotron, a microscopic switch that operated inside a bath of liquid helium at -452 degrees Fahrenheit. At this temperature, the components became superconductive, allowing them to switch states with almost zero electrical resistance and no heat. The technology held immense military potential. If perfected, the cryotron could provide the miniaturized high-speed guidance systems needed for the next generation of ballistic missiles. However, in 1959, following a visit from Soviet computer experts, Buck died suddenly at age 32. His death remains a point of intense historical speculation, occurring the exact same day a high-ranking colleague was also found dead. While the loss of Buck stalled the research, the cryotron ultimately faced a practical hurdle. The logistics of maintaining liquid helium environments were too complex to compete with the rapid, reliable scaling of the silicon integrated circuit. The transition to the transistor solved the heat and fragility issues of the vacuum tube. It allowed for much smaller switches, but it created a new physical limitation known as the tyranny of numbers. As engineers designed circuits requiring thousands and eventually millions of transistors, they hit a manufacturing wall. It was physically impossible to hand solder the millions of individual wires needed without introducing catastrophic errors. The solution was the monolithic integrated circuit. Instead of wiring separate parts together, engineers learned to carve both the switches and the interconnects out of a single solid block of semiconducting silicon. This move to a single solid-state object finally overcame the limitations of wiring, allowing the industry to begin decades of exponential growth. This growth followed a predictable path for 40 years, with transistors shrinking and clock speeds increasing. But in 2005, the industry hit a thermodynamic limit. After decades of steady climbing, CPU performance hit a hard limit known as the power wall. As components reached deep submicron sizes, they leaked current through quantum kenneling. Pushing clock speeds higher generated so much heat that chips would physically melt. This failure forced a shift in architecture. Since a single processor could no longer be made faster without overheating, engineers began linking multiple parallel cores together to share the workload. This shift toward parallel architectures provided the technical foundation for modern graphics processing units, or GPUs. AI training requires processing billions of data points simultaneously. This is only possible due to the parallel core structures adopted after the power wall. Today's AI data centers are once again facing the same thermodynamic constraints as the early mainframes. They require massive energy and complex cooling systems to manage heat from trillions of microscopic switches. From the first mechanical relays to the modern cloud, the history of computing is a series of solutions to physical bottlenecks. We are still manipulating switches, and our progress remains tied to the laws of thermodynamics.